Hello. Today we're going to take a look at topic 4.03, natural radioactive decay. Interesting. The word natural implies that there might be a form that's not natural. And there is. We'll take a look at it a little bit later in the unit. But for today, atomic vomit. Yeah, remember last time I was telling you about that? You had the vomit and then you had the verp, right? The vomit burp. Oh my gosh, that actually happened yesterday. It was so cool. I was sitting down watching TV and I burped and I had a strawberry like 2 hours before, and a little chunk of strawberry came back. Oh, it was amazing. Oh, I'm sorry. I didn't mean to gross you out. No, actually, I did. Anyway, so here we go. You may be familiar with the laws of conservation. There are three of them. The law of conservation of mass, which says mass can't be created or destroyed by physical or chemical change. Law of conservation of charge says that charge cannot be created or destroyed by physical or chemical change. And of course, then we also have the law of conservation of energy, which says that energy can't be created or destroyed by physical or chemical change. The reason I don't include energy is because it doesn't really apply to what we're going to do today. Now, when you're dealing with equations of any kind, you're going to have stuff on the left side and you're going to have stuff on the right side, and it's going to be separated by an arrow that points from left to right. In a chemical reaction, we call the stuff on the left side the reactants, and we call the stuff on the right side the products. But one thing that's always true is that if you add up the masses and charges on the left side and you add up the masses and charges on the right side, you're going to see that they always equal each other. This is why it's called a law. A physical law is an observation of something that's always true. Now, it doesn't explain why this is. It just describes that it is. And we're going to use that to our advantage today. Here's how alpha decay works. Alpha decay, and you can tell whether something undergoes alpha decay if you're in New York State simply by looking up reference table N and seeing if it has a decay mode of alpha. By the way, you'll notice here the 220 is the mass number, and it's also represented here as the mass number in the name of the isotope. Has a half-life of 27.4 seconds. More about that next time. But here's how this works. If you want to actually do the decay, the first thing you do is you write down the symbol and mass of the parent nuclide. So there it is, the symbol and the mass. But in order to complete this, we need to look up the atomic number of the nuclide. So the atomic number is 87. And we'll put that there. Because both the mass and the charge have to come out to be the same on both sides of the reaction. Next up, we'll draw an arrow. The nuclide we're starting with is called the parent nuclide. The nuclide we're going to end up with is called the daughter nuclide. No, not the son nuclide, always the daughter nuclide. And we'll also have the decay particle on that side of the equation. We write the notation for the decay particle. Now, if you don't know the notation for the decay particle, alpha decay, you can always look it up on reference table O in the New York State reference tables. It's 4/2He. The daughter nuclide, therefore, will have a mass of 4 less than the parent nuclide and an atomic number of 2 less than the parent nuclide, because the numbers on the top have to add up to the same thing on both sides, and the numbers on the bottom have to add up to the same things on both sides. So what plus 4 is 220? 216. What plus 2 is 87? 85. And therefore, we get our numbers. Is it still francium? Well, francium had an atomic number of 87. So whatever this is, it sure is not francium anymore. So what element does have an atomic number of 85? Well, that would be astatine. So we write its symbol after. And this would be the decay for francium 220. It works the same for anything that undergoes alpha decay. Whatever undergoes alpha decay will lose 4 in mass and will lose 2 in atomic number and become a new element. That's alpha decay. Next up, beta decay. Beta believe it! Cobalt-60 undergoes beta decay, so we're going to write down its symbol and mass. And of course, we need the atomic number, so let's look that up. It's 27. Then we draw the arrow and predict what the other side of the reaction will look like. We'll write the decay particles notation. Beta particles are 0 over negative 1e. Again, if you don't know this, you can go to reference table O and look it up. And the mass is not going to change because what plus 0 is 60? Well, 60. What plus negative 1 is 27. Now, you might be tempted to say 26 because, 26 plus 1 is 27. But I didn't say 26 plus 1. I said 26 plus negative 1. 26 plus negative 1 is 25, not 27. So what and negative 1 is 27? 28. The atomic number went up by 1 because a neutron was turned into a proton. Now, we don't have cobalt anymore. Element 28 is nickel. So we write that symbol down. And this is how you do all beta decay. The mass number will remain the same, but the atomic number will increase by 1 as the neutron loses its negative charge and leaves behind an extra positive charge. Keep an eye on this particle. It starts off as a neutron, spits out that beta particle, and turns into a proton. The total number of particles doesn't change, which is why the mass number remains the same. Positron decay. Calcium-37 undergoes positron decay. So we'll write that mass and symbol down. We'll look up the atomic number for calcium. It's 20. We'll draw the arrow. We'll write the symbol for decay particle. Positron is 0, positive 1e. Once again, the mass will not change. 37 equals 0 plus what? Or what plus 0 is 37? Well, just 37. What plus positive 1 is 20? Well, that's easy. That's just 19. 19 and 1 is 20. We no longer have calcium. What do we have now? We have potassium. So we write that symbol down. So look at this example here. Did you see what happened? Keep your eye on this particle right there. All right. We've got ourselves a proton. We're going to turn it into a neutron by getting rid of its positive charge in the form of a positron. The total number of nucleons remains the same, which is why we still have 37 of them. Except now, one of the protons has been turned into a neutron, and therefore the atomic number decreases by 1. And this is how you do decay equations for any radioactive decay. So, if you're in New York State, reference tables N and O will be your friends here. And we all need friends. Bye.